Welcome everyone. In this SOLIDWORKS simulation users primer for 3D Experience, we will be looking at the analysis of a crank assembly in both SOLIDWORKS and 3D Experience. In the previous video we covered how a physics simulation is organised. Now we will look at applying loads and boundary conditions. So let's get started. In the SOLIDWORKS study, there is the fixtures branch. This has predefined conditions for fixed geometry, roller slider and fixed hinges, then an advanced options for more complicated conditions such as specifying translations and symmetry conditions. Similarly, there is an external loads branch. This is where a variety of loads can be applied such as forces, pressures, gravity, etc. For both of these we will choose the type of feature we wish to add, select the geometry, then define any requirements such as the load level, a fixed geometry restraint on the outer surface of the pulley, and a 500 pounds force load applied to the handle in the horizontal direction. Even though we only have a single step, we could define a time history curve for the loading to get variation throughout the step time, although we won't do that here. In 3D Experience, the usage is very similar. There is just some terminology differences to be aware of. Fixtures are typically referred to as boundary conditions. We can progress to that tab in the action bar. Then, under the Applied Translation command, there are a stack of alternate boundary conditions. Fixed geometry in SOLIDWORKS is actually equivalent to clamp in 3D Experience, as both fully restrain all degrees of freedom. Fixed displacement is similar, except there is a choice for which degrees of freedom will be restrained. As usual, we can provide a meaningful name, select the support this feature will apply to, then choose the appropriate degrees of freedom and the coordinate system they act in. Then OK. Since this is a solid structural element, we only need to restrain the X, Y, Z translations, as these elements don't have a rotational degree of freedom. However, there is one additional aspect that we have to consider, which didn't come up in SOLIDWORKS. Because we have multiple steps in this analysis case, which step did this boundary condition get applied in? Well, it is the active step. This can be seen in the feature tree as the step which isn't grayed out and has an underline emphasis. In addition, there is a floating selector, which has drop-downs indicating the active analysis case and step. From these we can see that this boundary condition we just created is in the second step of the analysis. As such, this won't be present in the first step of the analysis. We could simply delete or undo this boundary condition, change the active step in the feature tree or the floating selector, then recreate it. However, there is an easier way to manage how analysis features are organised within steps, the Physics Manager. By default, this is usually visible on all action bar tabs because it is part of the Standard tab, which is pinned, which pins the display of those commands to each other tab. The Physics Manager will show all the analysis features in rows, then have columns for each step in the analysis case. Here we can see that the fixed displacement is indeed applied in the second step only, indicated by the bar. If we right-click on that bar, we get a context menu where we can edit, show, hide, etc. But also choose to deactivate this feature or start it in the previous step. Choosing that option, we can now see that this feature is activated in the first step then remains active in the second step. The physics manager is an informative dialogue of what happens across steps, but it can also take up significant viewing area of the display. It is a floating dialogue, so can be moved and resized. It can also be docked to the various sides of the display by moving until the blue background indication shows. Next, we will apply the load, but first we will change the active step to the first step. We then move to the Loads tab, where we see a range of types of loads to apply. These typically also have variations in the stacks accessible through the drop-down. Here we will apply a force, provide a meaningful name, then the X, Y, and/or Z force in the selected coordinate system. Note, unlike the force in SOLIDWORKS, you can freely type in the unit system as well, and it will get converted to the displayed system of units. So here we enter minus 500 pounds force. However, one aspect here is that we wish to change the load value in the next step. So we could also enter in a load value of minus 1 pounds force, i.e. a unit force, then use the scale factor to determine what load actually is applied, 500 in this step. We could also then specify an amplitude curve. This is the same concept as the time history curve in SOLIDWORKS, so that the load will change as the step progresses. These amplitude curves are defined in the Setup tab and then selected in the feature as needed. Note, in addition to directly using coordinate systems, the floating toolbar also provides alternate ways to define the load direction. Here we will continue to use the global coordinate system as it is convenient for this analysis. Now, returning to the physics manager, we again see that this force is applied in the first step with the bar icon. Then, since the bar continues into the second step, this force continues to be applied here as defined in the first step. This worked for the boundary condition, but we want to change that force for the second step. We can do that by right-clicking the cell and then choosing Edit in this step. This brings up the dialog where we can change the scale factor for this load. Since we applied a 1 pound force unit load, and in this step we want to increase to 1000 pounds force, we will simply change the scale from 500 to 1000. When we do this, we see that the physics manager icon has changed, showing the bar with a white diamond, indicating this feature is propagated into this step, but is also edited. As these are nonlinear static steps, that second step starts from the end of the previous step. So what is happening here is the first step ramps from 0 to 500 pounds force. Then in the second step the load ramps from 500 pounds force to 1000 pounds force. The second step does not start from the initial state of the analysis. Now we have a fully defined analysis case. 2 steps, a restraint on the pulley outside, a load that changes over the steps on the front arm, using the FEM which had FEM level contact defined. A common situation is that you wish to run multiple versions of the same analysis or very similar analyses. For instance, we may have a fine meshed FEM and a coarse meshed FEM and wish to do a mesh sensitivity study. Or we may have an alternative analysis problem where the load history is different, or the restraint is the rear arm instead of the pulley. We could simply create a new analysis case from the Setup tab of the action bar, but that would require defining all of the analysis features again. We can also duplicate the current analysis case to make a new one. This does prompt for the new analysis case, as well as which FEM this new analysis case will use. Here we will use the mesh captured version of the assembly to see what difference this has to the FEM bonded contact. Now we have a second analysis case, with all the steps, loads, etc. retained. We could use this as a starting point for another analysis changes as needed, but here we don't need any further changes. One aspect that having multiple analysis cases opens up is sequential loading. In particular, sequential loading involving different solvers. For instance, here we have an explicit analysis, forming a bent strip from an initially flat blank. This is a simple example of common deep drawing, stamping, etc. type processes, where explicit analysis tends to be the most suitable analysis approach, given the potential for significant nonlinear effects. However, once the strip has been formed, this isn't the final shape it will have. As the forming dies are removed, the elastic strains will relax and the shape will spring back slightly towards the original shape. We see that in this animation. This is significantly less nonlinear than the forming process, so an implicit static analysis is the more suitable approach for this. This can all be contained within a single physics simulation by having an analysis case for the forming stage. That will use a FEM with the original flat blank model, then a second analysis case for the springback stage. That will use a preloaded FEM so that the mesh is in the deformed state from the end of the forming and has the same elastic and plastic strains. In this example, we see why the more flexible approach of multiple FEMs, multiple analysis cases, multiple steps, and even multiple solvers helps analyze more varied problems. This does, however, mean that there are additional choices that you as a user need to make in order to determine how to set up any particular analysis. This is extra levels to consider than the more structured approach that SOLIDWORKS studies provide, but this more free-form combination of different concepts is what provides the flexibility to analyze different problems. Solving is fairly straightforward. Change to the Simulate tab of the action bar. You can do model and simulation checks, which can be very useful as the analyses get more complex to make sure there aren't any problems. But here we will simply solve. We get a dialog which defines how the solve will be done. First is the location. I'll assume you have cloud-based 3D experience roles, in which case you can choose to either solve locally using your own machine as resources, or you can solve on cloud hardware. Here we will choose to use that cloud hardware. Then there is the license type. This can be tokens or credits. Depending on what licenses you have, the available options will change. On this cloud tenant, for instance, there are only tokens, so that is the only option presented. Then we have a table for the analysis cases within this physics simulation. We can toggle these as to be solved or not as needed. When solving on cloud, the default configuration will determine a number of cores to solve based on various factors such as the type of analysis and size of the analysis model. If you wish to know what the default configuration is expected to be for your analysis, you can click Calculate Default Configuration. In this case, both analysis cases are small enough to be solved efficiently on 4 cores. The configuration updates to reflect this, although we can use the drop-down to select an alternative hardware configuration as needed. Many of the cloud roles have an embedded compute capability. This is the ability to solve on a certain number of cores, typically 4 or 8 depending on the role. This is for both local and cloud hardware. Here we see this in the estimate column. The first analysis case will require 0 tokens additional licensing because the 4-core configuration is within the embedded compute for my roles. However, the second analysis case does identify that additional tokens will be used. This is because embedded compute only applies to the first solve active at any time. Below the analysis case table, we see an option that is enabled to run the analysis cases concurrently, meaning both analysis cases will be sent to cloud hardware to solve simultaneously, so additional licensing beyond the embedded compute is required for that second solve. If we disable this option, then both analysis cases will be solved sequentially, so the embedded compute is again active for the second analysis case. Here, we click OK. The job is created for the solver and submitted to the cloud hardware. We can monitor progress by looking at the Iterations tab. There is also access to information files such as the data and message files. Once the analysis is complete, we can post-process, which will be covered in the following guide. To summarize, we can apply loads and boundary conditions in a manner very similar to SOLIDWORKS. Care does have to be paid when using multiple steps within an analysis case as to when and how these analysis features change over the analysis. In addition to having multiple FEMs within an assembly, we can also have multiple analysis cases within the physics simulation. Finally, for cloud roles, you can choose to solve either on cloud hardware or your local machine. Thank you for your attention.